Hi everybody, I'm Razvi. Welcome back to another video from the binary exploitation series. In this video, we will dig into two very important concepts in binary exploitation for ELF files, that is, executables in the Linux universe. These two concepts are the PLT and the GOT, that stand for Procedure Linkage Table and the Global Offset Table respectively. Understanding what these two binary sections are and what do they do is fundamental when performing attacks like return to PLT or GOT overwrites. In short, these two binary sections work together to make the actual execution of the binary possible. Specifically, they come into play when a function from an external library is called, firing a process that is known as lazy binding. In this video, we will see what lazy binding is and how the PLT and the GOT serve for this purpose. We will use a vulnerable binary as an example in order to understand what is going on. The binary can be exploited by abusing a format string vulnerability so as to perform a GOT overwrite and change the entry of a given function with the address of another one, hence hijacking the execution flow. However, the exploitation of the binary and the exploitation development won't be treated in this video, but in the next one. Here we will focus on the GOT and the PLT themselves from a binary exploitation perspective. And without any further delay, let's get right into it. Let us first see what file are we dealing with and what are its protections. We can see it's a 64-bit executable and it has been compiled with partial relro, partial relocation read-only. There are canaries present on a stack, the non-executable bit is enabled, and it isn't a position-independent executable. There are two main things that we care about in order to understand the GOT and the PLT. First, the binary is dynamically linked, and second, it has been compiled with partial relocation read-only. Everything we are about to see in this video doesn't apply if the binary is compiled with full relocation read-only or if it is statically linked. And now let us disassemble and debug this binary. First, I will use cutter in order to disassemble it. And let us take a look at the main function. As you may notice, there are a lot of functions being called that do not belong to the binary per se. For example, functions like puts or printf, which are functions from libc, and they are being used in this binary, however, their code is not present in the binary. In fact, we can see here that this binary is importing several functions. It is importing them from somewhere else. If we take a closer look at all these call instructions we have here, we can see that when calling setup and banner, which are functions that belong to the binary itself, they are defined within the binary, we can see that cutter is using a naming convention that starts with sim, that stands for symbol, and then the name of the function itself. However, in the case of puts, printf, read, and any other imported function, we can see the naming used is slightly different. That is, symbol, imported, and then the name of the function. We can see puts, printf, also imported, and we have here read, which is also imported. While it's true that this is just the naming convention Radara uses, or in this case cutter, it is an indication that this symbol is being imported from somewhere else. And how does this happen? How is the binary able to know the real address of the puts function that, remember, belongs to another library, which is dynamically linked, if the addresses of the functions from the library are different with every single execution, because that's what ASLR is for. And here is when it comes into play the Procedure Linkage Table, PLT, and the Global Offset Table, GOT. I will show you the most important aspects of the PLT and the GOT from the binary exploitation perspective. But before doing so, as always, there are tons of online resources that you can check out if you want to further your knowledge about this matter. I will show you just some of them that helped me back in the day understand what today we are doing in this video. Of course, you can find the link to these resources in the description of the video. The first of them is a video from RazviOverflow, of course, called Global Offset Table and Procedure Linkage Table. This is a very good video to understand what is happening into memory. Now, if you prefer written resources, text instead of videos, you can take a look at the GOT and PLT for pruning from System Overlord. We have PLT and GOT from Ironstone, which is of course focused on binary exploitation. We have Poon the GOT from Feng's blog. There is also GOT and PLT from CTF101. Then there is this discussion on reverse engineering Stack Exchange about what is PLT and GOT, a very interesting and elucidating discussion. We have also PLT and GOT, the key to code sharing and dynamic libraries from Tech Novelty. And finally, we have dynamic linking from the Linux Foundation. These resources will help you understand how the PLT and the GOT work together in order to make possible the execution of the binary. Now, however, if you really want to dig deeper and further your knowledge about what is all this dynamic linking thing, what is a linker, what is a compiler, I recommend you reading these two resources. The first of them is the Linkers series from Ian Lance Taylor. This series comprises 20 parts where he explains what a linker is and how does it work. And the second resource is a book called Linkers and Loaders by John Levine. If you read this book, you will for sure understand everything related to the linking process and the loading process. So let us go ahead and further study our binary. Now, what is this PLT, Procedure Linkage Table, and GOT, Global Offset Table thing? These two sections of the binary, because they are sections, as you can see here, we have the PLT and also the GOT. Here we have it. Are the sections in charge of resolving the address of a external function whenever our binary uses it. External function in this context means whatever function that isn't present on the binary, however it is imported and used by the binary. For example, functions from a shared library like GNU's libc, also known as glibc. And how do they work together? Well, let us take a look at our main function that we have right here in our code, and let us think about puts. Puts is a function that is imported from glibc. It isn't present in our binary, however, it is used by our binary. Whenever we perform a call to puts, as you can see, we are calling in fact sim.imp.puts, which isn't puts per se. What this is what's usually called in the context of software development a stub. It is a portion of the binary's code that replaces the real puts that this binary intends to call, of course. If we take a look at it, we can see that this stub performs several actions. It jumps to another address, and then it pushes a 0 on the stack and calls section PLT. Before talking about these instructions and what do they do, let us first discover where we are in the code right now. What section are we in? As we can see here in the right, we are indeed in the PLT section. The addresses that we are inspecting at this very moment belong to the range of the PLT section. In fact, if we go a bit higher, Cutter already identified this section. So we can see that whenever we perform a call to a function from a library, for example puts, our binary in fact is calling a stub from the Procedure Linkage Table. In this case, whenever there is a call to puts, it refers to this very address, which is the PLT entry for puts, and then it performs a jump to this address right here, which also belongs to puts. Let us inspect this address and see what this is. An address which contains a quad word value, which corresponds to yet another address. However, this address seems to point back to the PLT. But first, let us see where we are in the code right now. What section are we in? We are now in the GOT section. We are in the Global Offset Table. If we take a look at this address, we can see it belongs to the range of the GOT, the Global Offset Table. So when the PLT entry for puts is called, it first jumps to this address. And the value of this address is yet another address that we can see right here, which, if we consider its value and we take a look at the addresses, we can see it belongs once again to the PLT section. In other words, the PLT is jumping to the GOT and then it is jumping back to the PLT. And what is this address we have right here? Let us take a look at it. We can see it corresponds to the instructions that push a 0 into the stack and then call the very beginning of the PLT section. which we have right here at the beginning of the PLT section. And here we have a very strange code block. I won't go into what this code block is doing, but I will of course sum it up for you. What we are experiencing here, what we are seeing and following by this jumping back and forth from the PLT to the GOT and then back to the PLT, is nothing else than the process of resolving a dynamically linked function at execution time. This is called lazy binding or lazy linking, and it is performed every single time a linked function, a function from a library, is called for the very first time. The PLT, which is the Procedure Linkage Table, is the one in charge to call to execute the actual function from the library that the binary is trying to execute. In order to do so, it first jumps to the global offset table, which is a table of nothing else than just values of the dynamic addresses of the functions that we are trying to execute. That is, the functions whose addresses aren't resolved at linking time. They are resolved at running time, at execution time, whenever they are required. Since the puts function has never been called previously in this binary, the first time the PLT is jumping to the GOT, to the global offset table, the global offset table entry for the puts function is nothing else than value the address of jumping back to the PLT and invoking the dynamic linker in order to actually resolve that address. These code instructions right here that push a 0 into the stack and then jump to the beginning of PLT section, what are in fact doing is pushing a 0 into the stack and invoking the dynamic linker. The dynamic linker will then know what function it has to look for, and when the dynamic linker finishes looking for the puts function during execution time, it will place its actual address in the global offset table entry for that particular function, in this case puts. That very address will be placed in the puts entry of the global offset table, and this value will change. Then the real puts function, not the stub from the PLT, will be indeed executed. And from that point on, whenever our puts function will be executed, it will instead execute its PLT entry for the puts function, but only this time the GOT entry for the puts function won't point back to the PLT, because its address is already resolved, has been already resolved. So it will jump to the actual libc. So just to recap and to sum up, the PLT, the Procedure Linkage Table, performs the following two actions. First, if the global offset table entry for that function has been already resolved, jump to that address, which will belong to the library where that function is. And second, if the global offset table entry hasn't been resolved, invoke the dynamic linker, resolve that address, and then jump into it. That's how the PLT and the GOT work together in order to make the execution of library functions possible. Because remember that they are dynamically linked. They are linked at execution time, performing what is known as lazy binding. It is also important to bear in mind that the PLT contains actual instructions. The values of the addresses in the PLT section belong to actual instructions, whereas on the other hand, the values of the GOT section are nothing than just addresses. They do not correspond to instructions. They can't be interpreted as instructions. Now, of course, that's the theory. Let us see a practical example in order to better understand what is actually going on. I will use radare2 to disassemble our binary. And I will take a look at our sim.imp.puts function, which we have previously seen that it corresponds to the PLT section. Here it is, the PLT entry for our puts function. We can see it calls reloc.puts, which is this value right here, this address, which in turn corresponds to the GOT section, to the global offset table, in fact. And what I'm going to do is place a breakpoint right here. So whenever the puts function is called from our binary, we will breakpoint right into the Procedure Linkage Table. Remember that even though our binary calls puts, the real puts won't be called. It will call the procedure linkage table stub, replacing the actual puts function. This stub will in turn call the real function. In fact, let us seek that very address, position ourselves in that address, and if we ask Radare to print the address we are in right now, we can see we are in the PLT. And if we do just the same for this address, we can see it corresponds to the got.plt. That is the global offset table. If we take a look at all the sections this binary has, we can identify the procedure linkage table right here. And then we have the global offset table that is split into two sections, the GOT and the GOT.plt. We are interested in the GOT.plt. And why are there two sections with the GOT prefix? Well, it is because the global offset table is nothing else than just a table itself that contains addresses of the functions that belong to libraries. The GOT section contains the values that aren't being resolved in a lazy binding manner. They are resolved at linking time. On the other hand, the GOT.plt section contains all those values, the entries for every single function that is resolved during execution time in a lazy binding manner. That's why we are interested in the got.plt, and that's why the puts entry for the GOT belongs to the got.plt section. This of course makes sense because given that the GOT contains all kind of addresses pointing to external functions, not every single one of them will be resolved during execution time. That's why there's a difference between the GOT and the got.plt. Now let us first take a look at our main function, because we can see we have a puts call right here, right at the beginning. So let us execute our binary and see what is going on. We have hit our breakpoint, as we can see in the PLT. If we disassemble wherever our instruction pointer is right now, we can see we are indeed pretending to execute the PLT entry for the puts function. In fact, we are right here because we have placed the breakpoint. Let us execute each instruction individually to see what is actually happening here. Right after our breakpoint, we have executed the jump to the reloc puts that belongs to the puts entry in the global offset table. Since the value hasn't been resolved yet, it points back to the PLT. In fact, we can actually inspect it. As you can see, this is the global offset table entry for the puts function and it prints back to the PLT. If we continue the execution, we can see the next instruction will get us right to the beginning of the PLT section, which is where we are right now. And this is the code block that invokes the dynamic linker in order to resolve the actual address of the puts function in the libc library. And this is how the addresses are being resolved at runtime. Let us keep executing the code to see what is actually happening. Okay, we executed the jump instruction and we can see that the instruction pointer has already changed its address. So let us take a look where we are right now. If we disassemble the instructions we are about to execute, we see this very strange piece of code that belongs to what appears to be a process called LD. If we inspect the map memory for the binary right now as it is, we can see that we are executing a memory area corresponding to a program, a process called LD-2 whatever. So we have already jumped out of our binary and we are executing something else. In case you don't know, this LD process is nothing else than the linker itself. LD is the GNU linker or GNU's linker. If we continue our execution until we reach the breakpoint once again, because we have seen a puts has been already performed, we got printed this thing right now. We have hit a breakpoint once again because puts has been called again. Let us take a look at the values of the GOT table. Remember, we can simply print its value like so, and as you can see, right now it has been resolved to a dynamic address. This is an address that corresponds to the libc function. If we once again take a look at the map memory for this binary, we can see that this address starting at 7F30 ending in the E0 corresponds to 7F30. As you can see, the libc process has now been resolved by the dynamic linker, and whenever puts is called from our binary, it will jump to the PLT, which will in turn jump to this address we have right here, because the global offset table for the puts function now points to its actual address, to the address of the real puts function in glibc. In fact, if we take a look at the global offset entries for every other functions that haven't been called yet, for example printf, read, system, we can see that all of them, they point back to the PLT, specifically to the instruction that pushes the value that will be resolved by the dynamic linker. And that's how addresses of library functions are being resolved during execution time. That's how the PLT and the GOT work together. Now that we have seen what the PLT and the GOT do, we can talk briefly about what the logic behind the GOT overwrite attack is. We know that whenever our binary calls an external function, a function from a library, it will in fact call its PLT entry, for example puts. And puts will in turn jump to the contents of the GOT entry for that particular function. For example, the GOT entry for the puts function in this case is this address. This will be the address where the PLT will jump to. If we are able to overwrite this value with the address of any other function we like, whenever the binary calls puts, it will call the PLT entry for puts, which will in turn jump to the function we have just specified, to the address of that function. That's how we are able to hijack the execution flow. Please notice that we are able to overwrite GOT entries, first because we have a vulnerability that allows us to do so, for example a format string, and second because this section is actually writable. As you can see here, the GOT section is readable and writable. It has both permissions, which in fact does make sense since addresses are being resolved at runtime and GOT entries for these functions change whenever the dynamic linker is invoked. And remember that this kind of attack is possible whenever the binary is compiled with either partial relocation read-only or without relocation read-only at all. Now, if you want to know how this binary can be exploited abusing a format string vulnerability in order to overwrite GOT entries, I recommend you watching the next video in the series. I remind you that you can find a link to the binary exploitation series playlist I'm creating in the description of this and every other video from the series. I hope you liked the video and found it useful. If there's anything you want to say, leave a comment below, and remember, exploit code, not people. See you in the next one. Until then, GG.